making a video about the LeetCode problem 162, find the peak element. This question asks you to find peak element from an array. For example, 1, 2, 3, 1, the peak element, the index of the peak element is 3. A peak element is greater than its two neighbors. So 3 is greater than 2 and greater than 1. So this is a peak element. And in the second example, there are two peak elements. The first one is 2, the second one is 6. You can return either of them. Return the index of either the peak elements. So in this case, it returns 5, which is the index of 6. And it asks you to implement an algorithm that runs in log n time, which is clearly a binary search. And but this array is not sorted. So I was confused about how to apply binary search on this. Took me a while to figure this out. Yeah, so if you pick any of this, the number from the array, there are actually 4 cases, 4 possible conditions. There are 4 possible relationships between an element and its two neighbors. Let me draw. So the case 1 is, the number is greater than both of its neighbors. In this case, the element I is a peak element, so we can just directly return it. The second case is I is greater than I minus 1, but smaller than I plus 1. And in this case, we can just keep searching the right half. We can skip the left half. Why? Is because if I plus 1 is greater than I, then it's sure that you can find a peak element on the right half. For example, if the array keeps going up, we know that the left and right border are infinitely small. So this number is a peak element. And if it doesn't keep going up, instead it goes down somewhere, then we know this is the peak element. So in this case, in the case 2, if numbers I is smaller than numbers I plus 1, we can search the right half, which means, imagine this is mid, right? Yeah. So if this is mid, we just point mid to I plus 1. So this is a basic idea of the binary search. And case 3 is the opposite, which I is smaller than I minus 1, but greater than I plus 1. In this case, it's sure that we will find an element on the left half, so we can ignore the right half. So in this case, if numbers I is smaller than I minus 1, we will search the left half. So mid is I minus 1. In the last case, which is the case 4, the I is smaller than I plus 1, I minus 1, also smaller than I plus 1. So in this case, you can search either left or right. So we can choose to search to the right half. If in this case, we actually merge case 2 and case 4, right? And if you choose to search the left half, you can merge case 3 and case 4. And in this case, we just choose to search right, which is numbers I smaller than I plus 1, search the right half, right? Yeah. So this is the basic idea of why we can apply binary search on this problem. For each element we choose, we can always choose to search on one half of the whole array and skip the other half. Let's take a look at the code. I'm just going to copy paste the code here. So we are going to define a left and right. The left point to the head of the array, and the right point to the end of the array. And we keep this binary search until left equals to right. And the mid is equals to left plus right divided by 2. And the value mid is equals to numbers mid. And the value, for example, if the mid is 1 here, and its left is integer minimum value. Otherwise, it equals to numbers mid minus 1. Same for the right. If it's out of bound, for example, here, then we define it as integer minimum value. Otherwise, it equals to numbers mid plus 1. And if the value mid is greater than the left one and greater than the right one, then it is a peak element. We just return the mid, which is the index of the peak element. And if the mid value is smaller than the right value, which is the case 2 and the case 4, in this case, we move the mid to the right side. Sorry, we move the left to the mid plus 1, because we just need to search the right half. Otherwise, we are going to search the left half, so we point right to mid minus 1. And eventually you can return either left or right, because they point to the same element, which is a peak element.